Alrighty guys, so today we're going to be talking about something called most common ions. So before you get started, just make sure again that you're taking notes and that you have a periodic table out. I have one on the screen, but it'll be very helpful if you have a physical one next to you so that you can follow along and try out the problems through the video lecture. Okay, just to warm up, we're going to be drawing the Lewis structure for two different atoms. First, we're going to be doing it for neutral magnesium, and then we're going to be doing it for Mg2+. Okay, after that, we're going to talk about the valence electrons and the shells. Now, before we draw the Lewis structure, I want to just draw the shell model for regular magnesium. So if you guys are pretty confident with doing that, just go ahead and feel free to draw the shell model for regular magnesium. Okay, magnesium is right here on the periodic table. It's in the third row, so that means it has 3 shells. So that means I have to draw Mg, and since it's on the third row, it's going to have 3 shells. Okay, so we're going to draw 3 circles around it. Okay, so regular Mg has 3 shells. Now, for the electron or the protons, we know that it's 12 protons since it's the number 12 on the periodic table. And since this Mg is neutral, there's no charge. That means we have the same number of electrons. Okay, so we're going to fill in the electrons from the inside out. So we have 1, 2 in the first 2 shells. We have 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then we have our last two, 11, 12. Okay, so we know where to or how many to put in each shell because we count the boxes in each row on the periodic table. The first row is the first shell, and there are 2 boxes, so there are 2 electrons. The second row is the second shell, and we know that has 8 boxes. And then for the third row, we know that there's 8 boxes, so it can hold 8 max. So this is how we know the maximum number of electrons that can go in each shell is just the boxes in each row. And magnesium has 12, so we have 12. So this is a shell model for magnesium. So if we want to go from the shell model to the Lewis structure, okay, what we have to do is we only draw the valence electrons. The valence electrons are the electrons on the outside shell. So if you look at magnesium, it has only 2 on the outside shell. That means that the Lewis structure for magnesium is just going to be 2 valence electrons. So this is the shell model. This is the Lewis structure. And if we're going to answer the valence electrons and the shells, regular magnesium has 3 shells, right? Because there's 1, 2, 3. And it has 2 valence electrons. Alright, so that's regular magnesium. Okay, and we knew that it had 12 protons and 12 electrons. Now, we did regular magnesium. Now we have to do Mg2+. Now the thing about Mg2+ is that it has a charge. It's not neutral anymore. If you notice here, there's no charge. Mg2+ has a charge. That means that the number of electrons is going to change. Since Mg2+ is positive 2, we know from our formula that charge is equal to the protons minus the electrons. If the charge is positive 2 and it's magnesium, we're going to plug in 12 protons, so 12 minus the electrons. So the question becomes 12 minus what equals 2? Okay, if you do that in your head, you'll notice that it's 10 electrons. Another way you could think about it is if it's positive 2, that means it loses 2 electrons. That means Mg2+ has 12 protons and 10 electrons. Right? That means it has 2 less electrons than Mg. Alright, so before we can do the Lewis structure, let's just think about the shell model. Okay, so if we look at the shell model, we notice that there's 2 electrons in the outside shell. Now, we said that in order to go from Mg to Mg2+, we need to lose 2 electrons. Now, if we lose 2 electrons, we have to take away electrons from the outside shell. We always want to get rid of the electrons from the outside in. So if we get rid of the 2 on the outside, so for example, if we get rid of 1, 2, you'll notice that there's no electrons in the outside shell anymore. That means the only thing that we have left if we take away 2 electrons is the first 2 shells. That means that Mg2 plus, since it's basically Mg, but you're taking away 2 electrons, it's going to be Mg2 plus, and we're going to just draw 2 shells because we're going to have 10 electrons. Okay, so again, if we take away 2 electrons here, if we take away electron 1, 2, we only have this, which is Mg2 plus. Now, one thing I do want to mention, because I've noticed some people in their assignments haven't been doing this, you have to write the charge in the middle of the shell structure and the Lewis structure. Okay, so if we want to draw the Lewis structure for Mg2 plus, we need to draw the valence electron. So there's 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And so that means that Mg2 plus is going to have 2 shells, 1, 2 shells, and it's going to have 8 valence electrons. Okay, so that's the difference between regular Mg and Mg2 plus. If you take away 2 electrons, you get rid of the outside shell, and so it's only going to have 2 shells, and so the outside shell is going to be this in the second shell in regular Mg. All right, so that's pretty much review. What we're going to do today is we're going to be talking about what atoms like to do and what kind of ions they can become, right? Because technically Mg, right, it could become 2 plus like we have here. It could also become plus 1. It could become Mg2 minus, Mg minus, right? There's all these different charges we can get. We can get Mg3 plus, Mg3 minus, but the thing about atoms is that they have something called the most common ion. Okay? And so the most common ion is basically the atom or the ion that the atom most wants to be. Now, this thing called the MCI, the most common ion, which I'll abbreviate as MCI, these things exist because of 2 reasons. So atoms, they don't like having incomplete shells because they're unstable. So when we looked at the example with Mg, right? Mg had 3 shells, and in the outside shell, it only had 2 electrons. Okay, but we know from the periodic table that the third shell, it can hold 8 electrons because there's 1, 2, 3, 4, 5, 6, 7, 8, right? There's 8 boxes. That means that the third shell, it can hold 8 electrons max. So the max electrons this third shell can hold right here is it can hold 8 electrons max. But if you notice, it only has 2. Since there's only 2, that means this shell right here, this outside shell, is unstable because it's incomplete. So what atoms try to do is they'll either try to empty or fill up their outside shell in order to become an ion. And that ion that they become by either emptying or filling up is called the most common ion, or the MCI. Okay? So basically the only thing you need to remember is atoms, they either try to empty or fill up their shells so that their outside shell is always holding the max electron. So here, Mg can do 2 things. It could either gain 6, right? Because if we gain 6 electrons, we can go 1, 2, 3, 4, 5, 6. And if you notice, this outside shell is now complete. Or what it can do is it could lose 2, right? Because earlier we only had 2. So if we lose 2 electrons, we can get rid of 1, 2. And then if you remember from earlier, this shell, the second shell, was complete earlier. So since this is a complete shell, it's not going to be unstable anymore. It's happy and it's ready to go. So basically, we just need to decide if it wants to gain 6 or lose 2. We'll talk about how to figure that out in just a second. All right, so let's talk about how we can draw the shell model for an MCI. And we're going to do that with an example. Alrighty, so we have this table here, and we're basically just going to fill it out. We're going to start off by doing the column on the left, because the left column is easier. We're doing regular sodium. So if you go to the periodic table, we're going to look for sodium. And if you notice, sodium is right here all the way on the left. Okay, so we're going to write the symbol for sodium. The symbol is Na. Okay, the symbol for sodium is Na. Sorry about that, guys. That was my phone. Okay, we're going to write the protons for sodium. If you look at the number on the top, it's 11. So there's 11 protons. And it looks like this sodium isn't positive or negative. So that means it's going to have the same number of electrons. Since it's neutral, it's going to have 11 electrons. For the shells, we need to look at which row it's on. Sodium is on row number 1, 2, 3. It's in the third row, so it's going to have 3 shells. And then for the valence electrons, the way that we figure this out for a neutral atom is we just figure out which box in that row it is. Sodium is the first box in the third row. It's the first box in this row, right? This is row number 3. Since it's the first box, it's going to have 1 valence electron, which means that the Lewis structure is just going to have 1 dot. Okay? So if you guys need a little reminder, the shells, we figure that out by the row number. The valence electrons, we figure that out by the box number in that row. So if you look at sodium, it's the first box in the third row. So it's going to be 1 valence electron because the first box in the third row. Okay, now we're going to do it for sodium's MCI. So what we're going to do is we're going to follow these rules right here to figure out sodium's MCI. So what we're going to do is we're going to draw the shell model of the neutral atom. The neutral atom is what we have here. It's Na. It's regular Na. So what we're going to do is we're going to draw the shell model for regular Na. Okay, so Na has 3 shells, right? Because it's in the third row. So we're going to draw 3 shells around it. Okay, we said earlier that it has 11 protons and 11 electrons. We also said earlier that the first shell, it can hold 2 electrons max. The second shell can hold 8 electrons max. And we said that the third shell can hold 8 electrons max. And we know this because of the number of boxes in that row. So the first shell, it has 2 boxes. You can't see helium, but there's 2 boxes in the first row. The second shell has 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8. That's why it can hold 8. And the third shell has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Or it can hold that 8 max. So all we're going to do now is we're going to draw these 11 electrons. We'll start from the inside out. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so if we look at this first shell right here, this first shell is happy because it has 2 electrons. It's holding the max. The second shell right here, it's holding, if you count, 8. So this shell is happy because it's stable. It's completely full. But if you look at this third shell right here, how many electrons are in the third shell? Okay, the third shell, it only has 1. Now, if you notice, the third shell can hold 8 max. That means this shell is unstable. So that means what sodium is going to do is it's either going to gain or lose electrons in order to make sure that its outside shell is completely full. So what we need to figure out is it easier for sodium to gain or is it easier for sodium to lose? So let's think about the options. So if I want to gain electrons, how many electrons would I need to gain in order to fill out this third shell? Okay, so just think about that. How many electrons do you need to gain to fill out this third shell? Well, we know that it can hold 8 max. So if I want to fill this shell out, I'm going to have to gain 1, 2, 3, 4, 5, 6, 7. So sodium, if it wants to gain to fill out the shell, it needs to gain 7 electrons. Okay, so if I want to gain with sodium, I need to gain 7 electrons. Okay, the other option is to lose, because if you notice, sodium has only 1 electron in the outside shell, right? So if I get rid of that electron, what happens to that shell? That shell disappears. And if you notice, this shell right here, the second shell, is already happy. It's complete. It's stable. It has 8, which is the max. So sodium would only need to lose, it would only need to lose 1 in order to become stable. So the options are sodium can become stable by gaining 7, or it can become stable by losing 1. Okay, so we basically need to choose which one is easier. And the way that we can figure that out is just go for the number that's smaller. Okay, losing 1 is going to be a lot easier for sodium. It's going to want to lose 1 rather than gaining 7 because the number is smaller. Losing 1 is a smaller gap to fill than gaining 7. So sodium is going to want, sodium is going to want to lose 1. And if it loses 1, the third shell disappears. So we can start filling out these numbers a little bit. Sodium still has 11 protons because it's sodium. The protons can never change. For the electrons, if I lose 1 from 11, it's going to be 10. How many shells does it have? It has 1, 2, because that outside shell disappears. Now for the valence electrons, how many electrons on the outside shell? There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8. Okay, now we just need to do the symbol and the Lewis structure. Now for the symbol, we just need to figure out what the symbol is going to be if I lose 1. If I lose 1 electron, I lose something that's negative. If I become less negative, I become positive. So the symbol is just going to be Na+. Okay, another way that you could do it is using the formula charge equals protons minus electrons. Since there's 11 protons, so it's 11 minus the 10 electrons. 11 minus 10 is negative or positive 1. And the Lewis structure, we just draw this right here. Na plus, don't forget this symbol. And then there's 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. All right, and there you go. That's how you figure out the MCI. So sodium's MCI, the ion that sodium wants to become, is Na+. Na wants to become Na+ because it wants to lose 1 electron. It wants to get rid of the electron so the outside shell can be completely stable. All right, let's move on to the next problem. Okay, so when you guys do your assignment today, you're going to have something that looks like this. You're just going to have a table, and you're basically going to have to fill out the table by figuring out the MCI. All right, so let's do the next example. The next example is oxygen. So if we take a look at oxygen on the periodic table, let me zoom in a little bit. Okay, so oxygen is on the second row of the periodic table. Okay, oxygen is right here. So in order to figure out oxygen's MCI, basically we need to figure out, hey, is it going to want to gain or is it going to want to lose? So what we're going to do is we're just going to look at oxygen, and let's start by drawing the Lewis structure. Okay, regular oxygen is on 1, 2, 3, 4, 5, 6. It's in box number 6. So it's going to have 1, 2, 3, 4, 5, 6 valence electrons. So oxygen, if you notice, it's in the second row, so that means it has 2 shells. And it has 6 valence electrons. Okay, so let's take a look at this second row. This second row is the second shell. What's the maximum number of electrons that can go in the second shell? Okay, we just count the boxes. There's 1, 2, 3, 4, 5, 6, 7, 8. So the second shell can hold 8 electrons max. So if it can hold a max of 8 electrons, that means that this oxygen right here is not happy. It's not happy because the outside shell, the valence shell, is not full. So let's try to figure out, is it going to want to gain electrons or lose electrons in order to become full? So like we said earlier, we can gain electrons to fill up the shell. If I have 6 valence electrons and the 8 is the max, that means to go from 6 to 8, I would need to gain 2. The other option we have is we can just empty out that shell. And by emptying, I just mean getting rid of all the electrons in the shell. So 1, 2, 3, 4, 5, 6. If we get rid of all the electrons, oxygen can become stable because the first shell becomes a new outside shell. So it could either gain 2 or lose 6. Now, we said earlier, we need to figure out which one is easier. Does it want to gain or does it want to lose? So look at the numbers. Which gap is easier to bridge? Gaining 2 or losing 6? Okay, hopefully you said that it's easier to gain 2 because the number is smaller. 2 is a smaller gap to bridge than losing 6. So oxygen is going to want to gain 2. 1, 2. So if it gains 2, what's the charge going to be? What's the charge going to be if it gains 2? Okay, so we can either do the math or just think about it logically. If I gain 2 electrons, I'm basically becoming more negative. If I become more negative by 2 electrons, that means my charge is going to be negative 2. That means oxygen's MCI is going to be O2 minus. The total number of electrons is whatever electrons you started with. Oxygen is number 8. It was 8 total electrons plus 2 since it gains 2. It's going to be 10 electrons. And for the valence electrons, we just added 2 to the outside. And if you notice, there's 8 on the outside now. How many did it gain or lose? It gained 2 electrons. And it still has 2 shells because all we did was fill up the shell. And we already drew the Lewis structure. So the Lewis structure should look something like that. Okay, so oxygen is the opposite of sodium or magnesium, the example we did earlier. All it's going to want to do is gain 2. Alright, so basically we just need to figure out if it wants to gain or if it wants to lose, and that's how we make our determination. Now there are 3 examples that we're going to do of ones that are a little bit weird. They don't really follow the rules. Okay? Alright, so the first one that's a little bit weird is neon. So take a second to look for neon on the periodic table. Okay, just a quick hint, it's going to be all the way on the right. Okay, so hopefully you guys found it, but neon is going to be on the second row all the way on the right of the periodic table. So if you guys can, take a second to draw the Lewis structure for neon. Okay, so draw the Lewis structure for neon. Alright, so neon is in the second row. That means it has 2 shells. Okay, and neon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So neon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Okay, let's try to figure out the MCI. So let's try to figure out if neon wants to gain or if it wants to lose. Okay, so neon is on the second row, so it has 2 shells. And the second shell can hold how many max? It can hold 1, 2, 3, 4, 5, 6, 7, 8. Neon, so the second shell can have 8 maximum electrons. Now if you look at neon, how many electrons are in the outside shell? Okay, you should notice that it's already full. It already has 8 valence electrons. So that means that neon is already completely full on the outside shell, and that means that it's completely stable. So that means that neon is a weird exception because it does not want to gain and it doesn't want to lose because it's already full. Another way to think about it is already stable. It doesn't want to gain or lose because if I take away electrons from neon, neon's unstable. If I add more, it's going to get unstable. So neon, for the MCI, you would write no MCI. So if you see an atom that already is full or stable on the outside shell, it's going to have no MCI. So that means all of these numbers, or all the answers for these boxes, are just going to be the same thing for regular neon. So if we take a look at neon, how many electrons is it going to have? Well, if you look at the number for neon on top, it's 10. And if there's no MCI, that means it's not going to want to gain or lose. That means it's going to want to stay the way it is. That means that neon is going to have 10 total electrons. We said earlier that neon looks like this, and there's 8 valence electrons, so it just has 8. It doesn't want to gain or lose, so we'll just write neither. How many shells does it have? It's in the second row, so it has 2 shells. And so for neon, we don't really need to do much work. We just need to make sure that we know that there's no MCI, and all the other numbers are just going to be the numbers for regular neon. Alrighty, let's take a look at carbon. Okay, carbon, let's draw the Lewis structure for carbon. Carbon is in the second row, so it's going to have 2 shells. The number on top of carbon is 6, so that means carbon is going to have 6 protons and 6 electrons. For the Lewis structure, we just count the boxes, 1, 2, 3, 4. So since it's on the 4th box, we're going to draw 4 valence electrons. So that means it has 4 valence electrons. So let's try to figure out, does carbon want to gain or does it want to lose? Okay, since it's in the second shell can have 8 electrons max, right? Because earlier we counted a couple times now that there's 8 boxes. So carbon has 4. So in order to fill up that outside shell, it needs to get to 8. So to go from 4 to 8, we need to gain 4. Or we can lose 4 in order to empty out this shell, because we can empty out this shell by just getting rid of 4. Okay, so let's try to figure out which one is easier, guys, to gain 4 or to lose 4. Okay, the numbers are exactly the same. Since the numbers are exactly the same, it's kind of hard to figure out, right? Because earlier there was either number was greater for gaining or the number was greater for losing. But here the numbers are completely equal. And so if the numbers are completely equal, carbon wants to do neither. So carbon also has no MCI. So if you guys see an example where the number that you need to gain and the number you want to lose are the same, there's also going to be no MCI. It's not going to want to gain or lose. So that means all the numbers we can just write the same as regular carbon. Carbon's going to have 6 electrons. It's going to have 4 valence electrons. It's going to have 2 shells. And the Lewis structure is just going to be for regular carbon. Okay. Alright, the last weird example, and this is the one that you're going to have to memorize, is for hydrogen. So take a second to look for hydrogen on the periodic table. Okay, and try to draw the Lewis structure for hydrogen if you guys can. Alright, so hopefully you guys saw that hydrogen is on the top left, and so that means that hydrogen, since it's the first box in the first row, it's going to have just 1 dot since it's the first box. Some other facts about hydrogen: there's 1 proton because the number is 1. Since it's neutral, it's going to have 1 electron to balance it out. And it's on the first row, so it has one shell. Okay, so let's try to figure out, does hydrogen want to gain or lose? Now, if you notice, hydrogen is in the first shell. The first shell can hold 2 electrons because there's 2 boxes. It can hold 2 max electrons. So hydrogen, it could either fill up the shell, so to go from 1 to 2, you could either gain 1, or it can lose the shell by losing 1. Now, we said earlier that if the numbers are equal, there's no MCI. Hopefully you guys remember that from the example with carbon. But hydrogen is not like that. Hydrogen is a little unique. So you're going to have to memorize this one. But hydrogen is always going to want to lose 1 electron. Okay, so hydrogen is going to want to lose 1. And this is just something that you're just going to have to memorize. So if we lose 1 electron, if I lose an electron, if I lose something that makes me negative, that means I'm going to become more positive. And if I lose 1, I'm going to become positive 1. So hydrogen's MCI is going to be H plus 1. For the total number of electrons, we said that there's 1 electron. If we take away 1, it's going to have 0 electrons. And for the valence electron, if we take away that valence electron, there's no more electrons around it, right? H plus is going to have no valence electrons, so it's going to be 0. If you notice, there's no more shells, because if we get rid of the electron, there's no shells. So there's going to be 0 shells. So the Lewis structure for H plus is just going to look like this, H plus. All right, so just make sure you guys remember those 3 special cases. But other than these 3 special cases, where it's already full, carbon where the gain is equal to the loss, how many you want to lose, and hydrogen, other than those 3 different types of cases, you're going to just have to look at the numbers. Is the number for gaining bigger, or is the number for losing bigger? And it's going to go that way. Alrighty guys, so hopefully that was helpful. I'm on the Zoom call right now, so let me know if you guys have any questions. But best of luck to you on today's assignment, and we'll see you next time.